Okay, I think we're going to go ahead and get started. There's going to be some more folks joining us from the other meeting invite, but I think we can go ahead and get started. So, good afternoon. Welcome to the third of the 2025 DoD EMDQ workshop webinars. My name's Janice Willey. I'm a chemist with the NAVSEA's O4Q Laboratory Quality and Accreditation Office and the chair of the EDQW's Chemicals or Emerging Concern subgroup. Today's session is on my favorite topic and yours, PFAS. Yes, that's right, y'all. For the 11th straight year in a row, the EMDQ workshop is including presentations on PFAS at your request. Adam, if you want to go ahead and go to the next slide. In case you're not familiar with what the Environmental Data Quality Work Group does, it develops and recommends strategies related to sampling, testing, and quality assurance for environmental programs, coordinates the exchange of information among DoD components, develops DoD issuances to implement environmental data quality, and promotes cost-effective government oversight, and implements and provides oversight to the DoD ELAP program. Next slide. As I said, this is the third session of a 3-session EMDQ webinar series. Hopefully you were able to join us for the 2 previous sessions, but if not, you haven't missed out. Recordings of those 2 sessions, as well as this session, will be made available to you on the EDQW's DENX page. Next slide. Today's session will include presentations by 3 presenters on the topics that I am sure you have come up in your PFAS journey recently. Things like expanding analyte lists, especially the newer Flynn class of PFAS, ultra short chain PFAS, and the evaluation of precursors using top assay. We're going to have this agenda is a little fluid. We're starting a little bit later, and so we have plenty of time for questions. We had one presenter that was not able to present today, so we do have plenty of time. If we can go over, a little bit past 2:40 if needed. Go next slide, please. Just a bit on the logistics for today's webinars. Cameras and microphones for all attendees have been disabled. I do personally love to hear y'all's kids, dogs, and birds. 200 plus birds and dogs and kids could be a bit distracting. Please submit content-related questions or responses via the chat function as they pop up into your brain. Do not please put technical issues requests in the chat. For those, just please email the people that are listed on this slide. And as I said earlier, these webinars are being recorded and will be available on EDQW's webpage as soon as possible. Okay. With that, I thank you all so much for participating in today's webinar and strongly encourage you to play Stump the Presenter and post your questions as they pop into your brain in that chat. First on the docket today is Bharat Chandramouli, the Product Director of North America SGS. He's a senior scientist with 20 years experience in POPs and CECs, including PFAS, and is a published author on peer-reviewed articles and book chapters on atmospheric chemistry, PFAS, analytical chemistry, CEC's occurrence and fate, metabolomics, and more. And with that, I'll let you take it away, Bharat.
Thanks, Janice. Great to be here. It would be wonderful if we were in person, but we will do this virtually. So I'm just going to quickly share my window here. Just bear with me. And there we go. Get this in presentation mode. And off we go. So that's, as Janice mentioned, we'll be talking extending PFAS lists because, we're never quiet or never stationary. So, bear with me as we go on a journey with this. Photo of this cat. This cat is my coworker. We've had her for about a year, and she's always very exciting. I have another one. This looks exactly like that, but she wasn't still enough for me to take a picture. So there you go. She's not in the room, so no disturbances today. we've done my bio, don't have to bear with that. So just a little bit of history before we keep moving forward. And this is not much news to anyone. It's just that the list of US interest and especially global interest has been expanding as we move forward on PFAS. We started with two. I didn't have room, so I didn't start with that. We started with PFAS and P4. But as we moved through USCMR3 with the first EPA method that came up, and then additions to the method, and then new methods, one trend we have seen continuously is that the number of PFAS that we are measuring, target PFAS measuring, has always kept going up. EPA 1633, which was the last EPA reference method that came out, set up at 40, a list of PFAS that it included. So the first few methods were primarily just the terminal carboxylates and sulfonates. And then as we move forward, we've started adding more precursors. We've started adding more ethers. So that's, again, been a general trend and a trend that just will keep continuing, I assume. But 1633 is a good example of a mix of precursors and terminal acids that you will see in a typical method. Carboxylates, sulfonates, fluorotelmer sulfonates, fluorotelmer carboxylates, legacy sulfonamides, ethers, and so there you have it, a good mix. So that's good. We all worked very hard on 1633, and we did quite a bit of work on validation and done a lot of sample analysis in the last few years. And the good news is 1633 with a new A on in front of it is being promulgated. So there's a lot of information on the website there that you can look at the methods. So with that, I think I will conclude this presentation because we're done. There's no more PFAS analytical work to do. 1633 was supposed to take care of it all. But unfortunately, that's really not what happened. We've as we mentioned, the work never stops. A lot of our attention on targets beyond 1633 has been driven by new screening levels, driven by new toxicity information. So this is this one example of 3 new targets that have come up since 1633 was written, for which the EPA released regional screening levels. TFSI, which is a short chain sulfonamide type PFAS, used quite heavily in battery, lithium-ionic batteries. Perfluorooctadecanoic acid as C18, an extremely long chain legacy carboxylic acid, and perfluoropropanoic acid, a good representative of what we will be talking about quite a bit today, a little bit in my presentation and later in JP's presentation as well, part of the ultra short. So we go with these 3 additions, we go from C3 to C18. With a sulfonamide float in between. So once you see these new RSLs, people start asking for it because they need to start screening, and which means labs will need to start working on it. And we've been quite busy in the last 2 years, not just our lab, but many other labs working on new methods for this. So today's session really will be from me as kind of examples of how we've done what's worked, what's not worked. And again, I'm legally required to show you an iceberg slide, but these target lists are only a very small portion of what we're still trying to characterize from a list, whether you're looking at many hundreds, thousands, or many thousands, depending on whose definition. We're still talking a small portion of PFAS that we're still looking for from target analysis perspective. In some ways, again, I will show quite a bit of information towards the end of the presentation, where I see some of these expanded target methods where you're going from 5 to 6 to 40 to 80 or whatever you call it, as I would say bridging between what we have with standard reference methods and with the emerging technique of non-target analysis, where you're able to look for many, many more PFAS than you have standards for. And what the pros and cons of here are with these different types of approaches. With building expanded target analysis, which is the big focus of my presentation, the big advantages are that you can select specific targets to pick on. So whether they are new targets with screening levels, precursors that got missed from the 1633 list, I would say that things like phosphate PFAS DIPAPs from food packaging, or short chain sulfonamides, which have replaced the long chains in waterproofing treatments, HFF active ingredients, which are still not that heavily studied. These are non-ionic or non-anionic PFAS, which don't always go through the workflows that we have. The ultra shorts that we discussed briefly. But as you can see, this process is additive because every time you need to add a new target or new list of targets, you have to buy standards, you have to run validations, you have to add it to something or make a new list or make a new run. So in some ways, this has been the additivity and the process makes the scaling of new expanded target lists quite hard. The advantage, of course, is that you get quantitative information, quantitative definite information as long as you validate it correctly. The nice thing about non-target analysis, we'll talk about that a little bit, is that you're no longer restricted by this scaling standards validation process. You can start with a long list of suspects for which previous information is available. You can get quick qualitative or sometimes even semi-quantitative relative information. But in the absence of standards, you're still stuck with, yes, I found this, I really don't know how much. So in some ways, these methods, these expanded target list methods and non-target analysis, as we go through in the next few years, will be playing balancing roles and complementary kind of roles as we move forward. So that's just a little bit of background before we really dive into the chemistry and what happened. The nice thing from our perspective, especially as the 1633A, the last version prior to promulgation got written, was that we now have an EPA reference method that explicitly allows you to add new targets. That's the language of the method that I highlighted in purple there. So it says that laboratories may include additional PFAS as targets or alternate labels as standards become commercially available without the need to go back to the EPA every time you want to do this, as long as they meet validation criteria and the method criteria. So this is a big deal because what this enables you to do is to take a reference method that already exists, that has a good framework, that has a good validation backbone, and you start adding analytes to it as they become available, as they become important. Again, you cannot do this for every target. You will see this in our validation information, but as long as they are reasonably compatible with the weak anion exchange workflow of 1633, and they are for solids and tissues extracted using basic conditions, which is again a 1633 typical method workflow, you can add these methods to you can add these new targets to a method and still be under a reference method framework, which is again important when you're doing large scale information, when you're doing when you need data to inform policy. So lots of good there happened with just the addition of this one sentence, I would say, into 1633A. So a lot of what we are going to be talking about as we move through some of our validation data is under the assumption that these analytes are going to be added to some kind of 1633A expanded framework going forward. So before we dive in, little refresher on what 1633 looks like. If you have, if you've been seeing all our presentations for the last 10 years from all of our many labs and other partners, what you see in front of you is a typical best practice PFAS method, which now got written into an EPA reference method. You have isotopically labeled standards for isotope dilution. You spike the standard samples up front. For water samples, you do a pH adjustment to make sure you're near neutral, and then you run it through weak anion exchange. And weak anion exchange is mandatory for all analysis in 1633. So you can deal with matrix complexity and in the end, get an extract that looks the same, whether it's a solid, water, or tissue sample, and the use of carbon cleanup as well. With solids and tissue samples, it's a sequential basic extraction. The solids extraction is faster. The tissue extraction can take a little longer because of some equilibration times. But overall, the goal is to get these anionic and neutral PFAS that are 1633 targets into solution before you run weak anion exchange. And then, of course, once you get into LC-MS analysis, we all are familiar with the many QA/QC requirements that come both from 1633 and the DoD QSM framework. So the use of multiple transitions, ratio checks, injections recovery, and surrogates, injection internal standards for surrogate recovery monitoring, and all that. Use of bile acid checks as well. So overall, this is the 1633 framework in case you had forgotten what it looked like. And this is typical of the framework we will be using to check if some of these other targets we added to the method worked with those frameworks or not. So getting into what we actually did, we bought a lot of standards. And this was kind of the basic workflow that we went through when we were doing our optimization, validation, and rollout. First question is, does it work with the 1633A framework? Which means, do you get good recoveries through weak cation exchange? Does it survive carbon cleanup? Does it extract reasonably well with the basic extraction? Those are the three main criteria that you use. And if that works, then you can put it into a 1633A type extended method. So if that worked, we added it to our extended list method. And that worked for, you'll see, for a large number of targets that we looked at. In some cases, it did not work at all. For example, with the some of our cationic or zwitterionic active ingredient, HFF type PFAS. So for those, at this point in time, we just slotted them into a direct inject type framework where you are getting slightly higher reporting limits, but you're still able to report them. In cases where it partially worked, and that's the ultra shorts, we'll talk about that in a little bit. We put that into a different method for now. And in cases where it did not work at all, but we were still able to do it by LCMSMS, which is the fluorotelmer alcohols, we slotted that into a different method as well. So typically, for now, you can cover all of this with a 1633 type run, a direct inject run, an ultra short run, and an FTOH run. But we'll see that when we move forward, and in the next year or two, there's going to be further optimizations possible as well. That's in general what we were trying to do with all of these PFAS that we brought into our lab in the last few years. So before we go too far, this was the initial list that we are testing, and every few months this list expands because we get more standards, we start trying new things, and some of them work, some of them don't work, but we keep adding. So just want to spend a little bit of time on the list. First of all, this was an iterated process. So when we first started, TFSI wasn't in here, and then we added that kind of towards the end as the RSLs were published. So, but overall, we were trying to cover off some chain length extensions. So for our perfluoroalkyl carboxylates, the PFPRA, PFODA, and hexadecanoic acid, and TFA. Again, going from C2 all the way to C18. The perfluoroalkyl sulfonates as well, again, C1, and mostly extending on the ultra short ends, the C1, C2, and C3. You can also add other sulfonates, but they will work. We just haven't gotten that far yet on the C13 and beyond yet. Fluorotelmer sulfonates, 10-2 FTS. This was a reasonably frequently asked, like, why is this not in there in our list? So we added that. Fluorotelmer carboxylates as well. A lot of these are intermediates in AFFF degradation. So when you're looking at or any fluorotelmer degradation, really. So when you're trying to complete the picture, you want your fluorotelmer carboxylates in there as well. And 8421 has a couple of these in the ASTM method too. PFECHS, cyclic perfluorinated acid, it's a PFOS replacement. And after that, a whole bunch of phosphates that we see occasionally in samples, some more than others. The dipaps are ubiquitously present in solid samples. The other phosphates, not necessarily, but again, standards are available, so we put them in. The sulfonates, the short chain sulfonamides, these are, again, a lot of these are replacements for longer chain sulfonamides, and we find, especially in literature, find the FBSA, the metal FBSA, and the C6 as well, frequently detected in samples, so we want to put them in. The TFSI we kind of added at the end after the RSL became available. After that, it was a bunch of ethers for which we had standards, Naphions and the PFMOAs and the whole list, and a few fluorotelmer betanes as well. which are AFFF active ingredients. And then the fluorotelmer alcohols, this is, I just added in here, this was a legacy method that we'd already been running for a number of years, but so we didn't need to do much new development there, just wanted to add it there for the sake of completeness. And this again, all of this is run by LCMS-MS at the moment. So we did a whole bunch of validation. I am not going to bore you with the gory details of all the stuff we did, but it was usual validations with the IDOCs and the MDLs and the MSMSDs and whatnot. But typically what we found was out of this, I believe this is about 90 PFAS. I always forget. But out of this, the 50 or so we added, 35 worked pretty well with the 1633, whatever you want to call it, AA extended framework, and at pretty good reporting limits as well. So in that low nanogram per liter, low single-digit nanogram per liter range where 1633 sits at the default 1633 sample set. So that it's about 75 PFAS that we currently report that all meet a 1633 type reporting limit and other QA/QC criteria. We also added a whole bunch of labels because those were available and isotope dilution is always great. So those are also part of the method now. The direct inject method, we had 4 targets, the Nafion and the HFF agents, which didn't quite work well with the cation exchange. So they have higher reporting limits and smaller sample size, but again, they worked reasonably well when we validated them. Fluorotelmer alcohols, again, legacy method that we've been running for many, many years. The nice thing about this is that it does run by LCMS-MS, so you have fairly low reporting limits, which is especially important in aqueous samples because these are not high-level targets in aqueous samples. They tend to be more on the solid side, so that's there. Ultra shorts, we have 5 targets. I'll show you a little bit of data later on what worked, what didn't work. At a smaller sample size, again, there are some method limits here where this partially worked with the 1633 framework. I'll show you some info on what didn't work. But the one thing that I wish we had done a little differently here was that this was developed before the PFPRA RSL. So PFPRA was added to the ultra short method. It would work with the 1633 workflow mostly. I'll show you some data on what it looks like currently in the 1633 standard method. The fluorotelmer alcohols, they're just a completely different workflow. They extract differently, they analyze differently, they behave more like neutral semi-volatiles than PFAS, so you have to treat them like that. PFPRA. So the nice thing about running it in an ultra shorts method that we're currently doing is that the peak shapes look really good. It's reasonably well retained on the column we're using, which is a hybrid ion exchange and kind of C18 type column. So you can see that that's the peak shape on the left there, and that looks pretty good. What it looks like when we try and run it on our 1633 default method, which is the same as written in 1633, is that these look kind of, interesting is how I would call it. They're not retained at all on a C18 column. And you can do some things to optimize this. You can run slightly different column chemistries. You can extend and run. You can make a longer column. You can do many things. But this is what it will look like in default when you're not trying very hard. So if you have added PFPRA to your list recently, if you're looking at RSL data that's required because there's new RSLs, do look at the chromatography occasionally to see do the peaks look reasonable, or is the data looking okay? Because there's going to be a lot of noise in that section if you're running it in 1633 standard method. So that's a little side note about PFPRA. Ultra shorts, and I'm not going to spend too much time on ultra shorts because JP after the break will talk. I think his entire talk is on ultra shorts, so he will spend a lot more time on it. But what we were trying to do with our ultra shorts method, these are the 5 typical ultra shorts that added. This doesn't include TFSI that works with the 1633 list. Is that We were trying to first make it work with the VCAN exchange type cleanups because you can get lower reporting limits that way. You can use more sample. What we quickly found was that the chemistry became challenging. They are very short, so most of their interactions with the VCAN exchange column um, uh, are are not hydrophobic, they are more anion exchange. So with anion exchange, the it's a little bit more challenging to get the chemistry right, to get the timing right. So we were doing some sensitivity tests. We were testing some effluents and some river water samples to see how much sample size you could actually handle before you started losing recovery. And for some of these targets, TFA, especially trifluoroacetic acid, we really could not go beyond 100 mils in most cases before your recoveries went pretty much to zero. And PFPRA tended to behave similarly as well in a lot of the experiments we did. PFPRA was a bit more robust, but we still saw similar effects occasionally with PFPRA which is the third, the third one from the top there, the one in maroon. That river water sample, you see that at 250 your recovery is dropping very low. So a couple of things we did to optimize this. We did, for our ultra shorts method, run the VCAN exchange quite a bit differently than when you would run it in 1633. You run it slower, the conditions are a little different. And then at 20 mils, 25 mils, which is adequate to get good data for TFA or PFPRA. The method optimized really well. All that information is in an upcoming ASTM method for 5 ultra shorts. It's now in the hands of the ASTM undergoing balloting, so we've got some questions back. We've responded. So hopefully in the next months to a year, this method will be ready for multi-lab validation with the ASTM as well. So, and that will be available fairly soon. So if you want to take a closer look at this method as we move forward. So we wanted to test this data in a few samples. We started with the landfill leachate project because we love landfill leachates. They're full of PFAS and they're full of a nice variety of PFAS at reasonably high levels. So we get to have fun and look at some interesting data. This was two municipal solid waste landfills. One is an active site in operation since the 60s, and one site that was closed in the late 80s, I would say. We don't know the exact date. We ran, excuse me, we ran 5 methods for this. We didn't run the fluorotelmer alcohols. It was the EPA 1633 list, ultra shorts, and the 1633 extended list. So we didn't run the direct inject, we didn't run the fluorotelmer alcohols. And this was done before TFSI was fully validated. So we didn't add TFSI to this list as well. In this case, we ran both PFAS, the pre-top analysis, and we ran post-op PFAS methods as well. Won't share too much info from the post-op data, not the focus of this presentation. But the nice thing with our post-op method now is that we were able to extend the top assay to the ultra-short PFAS. So we added the 5 terminal acids to our top post-op assay as an option. So that it's a nice way to get better information on fluorotelmer degradation, because a lot of those fluorotelmers are going to trifluoroacetic acid and PFPRA as well after the top assay. So it makes your picture a little bit richer. So, we went through all the data and there's a lot of information here. You will see this is the active site. So the levels are higher because it's got more newer PFAS in it. You will see this immediately, and we're starting to see this more and more. Trifluoroacetic acid is what is labeled here as perfluoroethanoic acid, is the single largest PFAS at around 20 micrograms per liter in the sample. It's colored maroon there. Everything else is, I would say an order of magnitude or a little less lower. But this is fairly typical of what you would see in a landfill leachate. You have high levels of carboxylates and sulfonates because there's a lot of transformation going towards the end terminal products in the landfill leachate. So that's a typical pattern. You see a that full list of carboxylates available. You see a full list of sulfonates as well, nothing beyond a PFAS that was detected in the sample. The C1 sulfonate was the highest fluorinated compound detected. Again, this is not officially defined as PFAS in the US, it is in the rest of the world. So that's why there's a quote around PFAS there. But one thing that was interesting here, and in this particular sample, we didn't see any PFPRA. Again, we were very surprised and looked many times, but it was not there. Don't ask me what, not sure. Typical again with fluorotelmer carboxylates, you see the 3,3 and 5,3 FTCA at very high levels because those are again metal stable degradation products of fluorotelmers. So you see that in the landfill. That's this classic landfill signature. Want to point some attention to some of the non-1633 targets, so the ones in blue-gray there. What we mostly found in these samples were the sulfonamides, the short-chain sulfonamides, so the C6 and the metal substituted C4 and C6. And a little bit, I think it was a trace level phosphate there, but none of the other phosphates, they tend to be more reactive in landfill. So you see them reacting and going through the fluorotelmer degradation pathway. So you typically don't always find there's a lot of phosphate PFAS in these landfills. But again, this is fairly indicative of the trends we're seeing as we use this extended list more, is that especially the short chain sulfonamides are showing up more and more often in the samples that we analyze. Not surprising, they are waterproofing targets. So, the old Scotch guards with the C8s were replaced with the C4, C6, and the side chain polymer. So you expect to see more of these in the environment these days. Similar with the closed site, though different. It has been closed since the 80s, so the levels were well over an order of magnitude lower. Again, trifluoroacetic acid was the single largest PFAS in quotes found, and we found high levels of the C1 sulfonate as well, and also the typical fluorotelmer carboxylate pattern. Also, in this sample, you are seeing the sulfonamides at much lower levels, so these are low nanograms per liter. Not surprising. First of all, the PFAS load going into this landfill was likely lower, as you can tell from the overall pattern. But also, you'd see a list that is more loaded towards the CH type sulfonamides with the older carpets that were put in these landfills, had more C8 than C6 and C4 in them. So you would expect to see that pattern. Again, a small hit of the 8,2 PAP, but nothing else from a fluorotelmer carboxylic or from a phosphate list. And this one did not have PFPRA as well. I need to look at the PFAS chemistry to understand why it's happening. We did see a little bit of PFH, CHS, but very low level. Not really sure. We didn't see any ethers in these samples, which is, again, it's probably geographical and time related. Comparing the sites, nothing, as I mentioned, is really a function of the active site is active, has received more PFAS, so the levels are generally much, much higher at the site than in the closed site, which has been closed since the mid-80s or late 80s. So, and people still had all their carpets, so a lot of these carpets were not going to the landfills at that time. But both sites show similar patterns of precursor transformation. You see fewer precursors in the closed site, as you can tell from this stacked chart here. The active site has 41% precursors, whereas the closed site only has 14%. Again, function of how long it's been cooking. Ultra shorts are really the single largest class in all of these. So as we keep looking for these ultra shorts, we will always find them. Though most of these are TFA. So, if you don't think it's a PFAS, you may not need to worry about it. The 1633 extended list didn't pick up as much as we were expecting in these landfill leachate samples. But again, these are landfill leachates where you've been having a lot of reactions and going to the terminals. So that's not surprising. We had about 3% of the list by mass, by concentration in the active site, whereas it was just 1% in the closed site. But overall, the methods performed really well. We got good data out of these samples. So we were pretty happy with how these extended methods are performing right now. Since we did this pilot, which was this year or late last year, if I remember correctly, we've done quite a bit more work in effluents, influence biosolids, and ambient monitoring as well. So the data keeps coming in, and we are seeing that a trend that we see a lot of the short chain and sulfonaminds especially come up ubiquitously in a lot of these samples, and the DIPAPs come up quite often in biosolids. So some of these list items are not often detected, but some of them are always detected. A little bit of hit and miss there, but always when you're extending lists, that's going to happen. So that was our experience with all of this, fun parts of doing extended target analysis. We also recently got our hands on a non-target analysis, high resolution mass spectrometer. So we have been playing with that as well for the last 6 months or so, and color us extremely impressed. Recent generations of QTOFs and Orbitrafs have substantially closed the sensitivity gap. Obviously, there is still a sensitivity gap. We are able to calibrate 1633 successfully, not at the levels we always calibrated, where we calibrate 4 times lower than the method in our lab, but 1633 default calibrations are mostly achievable on this kind of system, which means you are looking at a high level of sensitivity, but also the ability to look at hundreds, thousands of PFAS. So this, from my perspective, this has worked really well. And this, as we move forward, we will maintain our extended target list to support quantitative analysis, to support regulatory analysis, to support places where you need concentration definitive data. But for a lot of our longer list monitoring, a lot of our initial look-sees where we're looking at hundreds of PFAS, we are slowly looking to shift into more of this untargeted space and more of the suspect screening and more of these non-semi-quantitative spaces. So far in our hands, we've been doing a lot of comparative analysis, 1633 run by low res versus high res. And typically the data compares across, 3-4 orders of magnitude. Again, these fairly high level effluent samples, we are able to get good comparisons at single digit nanograms per liter all the way up to 2000, microgram per liter or low microgram per liter ranges. So far, as we extend these lists, these high resolution methods are also working really well to push the boundary on what we can do. One interesting thing we are finding as we run into high resolution mass spectrometry is that we are able to detect interferences quite well. This particular test sample that we were running would have been reported as a proper 1633 run because the peaks met ratio, the surrogates look fine, the peak shape looks fine. But the minute we ran it in high resolution, we found the concentrations are actually about 3 or 4 times lower, depending on the sample and replicate. What we found after diluting our effluent sample and running it again using the default 1633 method was that the samples, the data was comparable again. So there was some unknown matrix enhancement that was going on that was causing this interesting thing. I wonder how often this happens. I don't think it happens very often, but again, as we move forward, in addition to using these kind of high resolution approaches for longer lists, longer suspect screening, the ability to use them for interference checking for definitive information, unless it's a very low level hit, a high resolution mass spectrometer can really confirm some of the "are you sure" kind of questions that we get asked all the time. So some interesting data, something to ponder on. The nice thing about HRMS is that you can also, if you set up a curve, you can quantitate hundreds of PFAS. You're not limited by space, you're not limited by time. You get full scan quantitative data for hundreds of PFAS as long as you have all of them in your standard mix and it calibrates. And yeah, we're able to run calibrations quite routinely for longer target lists these days, which is very nice. So I'm gonna conclude here with a little bit of time for questions. Building longer and longer target lists is arduous and gets expensive, but there are definite benefits for accuracy, precision, and data usability. So, target analysis, we're going to be using this for a long time, for longer lists as we move beyond 1633. The 1633 extended list points to an easy extension of this approach to other anionic and neutral PFAS, especially sulfonamides. I forgot to tell you that phosphates and PAPs and DIPAPs remained extremely tricky on LCMSMS. So, it's not always easy to get right, but it's possible, and ether acids as well. Early days, as I mentioned, and JP will talk about this a lot more, but if you look for ultra shorts, you will find them and close some gaps on top. I didn't show you top data, but it was definitely pretty interesting when we were looking at these leachates and other effluent samples as well. JP will talk about this a bit more, but if leachates are going into a wastewater treatment plant, not looking at ultra shorts will mean a significant underestimate of your own organic fluorine. So something to always pay attention to. And are we just in a stopgap for long lists before non-target analysis and suspect screening takes over? I don't know, maybe. That's a topic for active discussion. That's just the chromatograms are just, I'm just showing you what the peaks look like that in high res versus our typical 1633. Same concentration. This is the low level of 1633. You can see the peaks look perfectly fine and quantitative at those levels, even using high resolution. So these instruments are getting much better. So with that, we'll take some questions. Just leaving you here with my contact information so you know how to reach me, email, LinkedIn. If you call me, I may not actually pick up, but you never know. So, but definitely will respond to your emails. So with that, happy to take questions.
Great. Thank you so much, Bharat. That was really interesting. I think we have one question right now. So if you're considering high-res mass spec, are you also considering GC-MS-MS?
Yeah, I think we haven't bit the bullet quite yet, but as we will need to. The list of addressable PFAS, especially as you're looking at remediation, as you're looking at products of incomplete combustion, will need GC approaches to really fill the gap here. But we'll give us one more year.
FDOHs. Yeah,
Yeah.
FDOHs definitely. What do you consider to be the breaking point for number of analytes before you switch to TQ to high-res mass spec?
I think it depends on the instruments. We can easily look at 50, 60 targets. Beyond that, on a single run, what starts happening is you can put more targets into a single run, but you start losing sensitivity, you start losing points per peak, you start losing peak shapes. So there's ways to deal with that. You make the run longer. You can inject more. There's a few things you can do, but typically, again, we're looking at 70, 80 targets. If you're really looking at low nanogram per liter type reporting, that's our general trend. But there's newer instruments, the top of the line instruments that manufacturers do, which we don't always have access to, can do a lot better because they're faster and they're more sensitive.
How about with respect to the ultra chains and your extended lists? I know that some of the ultra chains can be a little bit problematic when it comes to decon blanks, field blanks, and even lab blanks and the contamination. Can you talk a little bit about your experience with those?
For sure. So out of the 5 ultra shorts that we measure routinely, I guess 6 including TFSI, if you think about it as not short, 5 of them have no blank issues. So PFPRA, the C1, C2, sulfonates, nothing. We never see them in blanks. Trifluoroacetic acid is a different matter altogether. I think it's either we have been generally lucky where we don't see it in blanks as often as other labs are reported and as other literature is reported, but occasionally we will see trifluoroacetic acid come up, especially more, I would say, in field and equipment type blanks and samples that have been or blanks that have been handled by more people than just us. Our water that we use in the lab is TFA free. It looks like we don't never get hits from that, but at the 50 to 100 nanograms per liter type levels. But it's trifluoroacetic acid is the exception. It is ubiquitous. It's raining TFA. It's everywhere. So you will see it.
We'll go ahead and go on. Okay, so our next presenter is Tiffany Hill. She's a senior technologist at Jacobs with over 20 years experience in the field as a chemist. Tiffany began her career at former CH2M Hill Applied Sciences Laboratory, where she led the semi-volatiles department, and later took on the role of laboratory project manager. As she transitioned into consulting, Tiffany played a key role in some of the earliest Priority 1 PFAS inspections, supporting over 20 installations. She's been deeply involved in PFAS research at Jacobs, contributing to projects funded by CERTIP and ESTCP. Tiffany also participated in the method validation study for EPA 1633, serving as both data validator and reviewer. Today, she's collaborating with other subject matter experts across Jacobs to launch an innovation studio in Corvallis, Oregon, focused on treatability studies and cutting-edge environmental solutions. With that, I'll take it away, Tiffany.
Thanks, Janice. Glad to be here today. Let's try to get this in the right mode for you guys. There we go. Sad that we can't be all together in person, but we will do the best we can with what we've got here today. Once again, talking about my favorite four-letter word. So we're back with PFAS and back with the top assay again today. And I will say, Bharat, I thought it was interesting that, even with expanding your analyte list, that you still use that as a tool to kind of capture what's going on big picture. So yeah, today just kind of going over, a little bit about the top assay, some of the background, where we've come from, how do we look at this data, what can it and can it not tell us clearly, because there's always some limitations within this, in this lovely game of whack-a-mole with PFAS. And then I just want to share some framework and data interpretation that we did here with a project of ours. The bounds that we put upon it, and how to evaluate that data, show you some examples. And then also within this, what I thought was interesting, we also had some AOF data. So just to kind of look at that in comparison with what the top data was telling us. And then where do we go from there, and maybe some things that we learned through the process. So background, a lot of us are all familiar with this and the evolution that is PFAS analysis. Back in the days when we didn't have all those QSM tables or a certified method, I look back on that fondly too, Bharat, when I remember, oh, there's a method coming. This will answer all of our questions. Yet, yeah, we're still chasing that. So, just through all those different versions, and, those of us who are trying to keep up on this and chase this with, different work that we're working on, and to help our, our clients and our partners to figure out this conundrum that is PFAS. So the top assay, the simplest way to think about this is just to kind of capture those other PFAS that we don't have a direct standard for. Over the years, it seems like there's always just this catching up, and, as Bharat mentioned, trying to buy new standards and see what's available and keep up on that, because, this is constantly evolving. But the other, and if you look at that whole family tree of all the potential compounds, there's a lot that we could be looking at. But by using the top assay, what this does is it will examine some of these potential transformations. Because clearly out in the environment, that's a whole other element to consider of what could happen, what did happen, and so forth. So the great thing about using this technique is we're still using the things that were already available, just, essentially just doing an extra digestion to kind of see a before and after comparison. I mean, I'll have to confess, I know when this first came out, I was personally doing this top assay before the labs were even offering it. So thank you all for doing that now, so I don't have to anymore. But you know, just like all the visuals that we've seen over time, and you see here with the little, you know, they look like little icebergs to me of, you know, what we could see versus what we did see, and just trying to close that gap and capture more of this contaminant. So I know there's a lot of, you know, trees and maps that show all the potential transformations. I know there's some pretty complicated ones. I didn't want to make you go cross-eyed trying to see those today. But here's one of our, you know, simplified looks at some of the precursors and some of the things that they can transform to. And then as you'll see, as we go over what I have here today, we have some of these little heat maps with the 3D fingerprint plots to kind of visualize before and after, what's happening, what disappeared, what increased, and so forth, just based on what happened through the top assay. And so, you know, like I said, this is a very simplified version, but hopefully this will be a simpler demonstration so that way none of our brains hurt. So, okay. You know, as it was, we've all looked at different laboratory data, and we all have the best expectations that everything's going to go perfectly. So what does this good data look like coming from the top assay? So once again, this is like ideal scenario. Everything goes perfectly. This is what you're going to hope for. So that, you know, one, there'd be none of the perfluoroalkyl acid precursors that are detectable. So it shows that the oxidation was complete, everything was converted, we're good to go. I can say I've had some personal experience where that was tough. But also that you want your total, you know, I can say this in air quotes, if we were in the same room, you'd see me doing that. That post-top assay, your concentrations overall are going to be greater than pre because you've transformed and captured some of those analytes that you couldn't previously. And then also that you want your carboxylic acids to be greater than they were initially. So you want, you know, post-top to show that we did transform some precursors into those PFCAs, and you're capturing that and measuring that, all looks good. And then also just something to examine and that we used through this process was looking at the sulfonic acids, and that those didn't really change much because overall, that's not what this assay is generating for us. So if those are similar, it shows that things went according to plan. But as you all know, we work with environmental samples. They're not going to always work the way we want. I mean, if you were here on some of the previous sessions and you saw some of the pictures from Dr. Choike and, you know, the different looks at what was, quote, a groundwater sample. I know we've probably all collected some of these. We've seen some of these at the lab, and it's not ideal. So despite all of our best efforts, you know, collecting these samples, it doesn't always go according to plan. We're not dealing with the pretty stuff here. So how do we kind of walk this back and look at this with kind of a real look at what's likely to happen? What's more realistic here? We know we're not going to all be dealing with pristine samples. So in theory, as we talked about before, those PFAS precursors should be gone. They should be oxidized. But like I said, there's other things that are competing for that oxidant. And, you know, I know the laboratories put in certain spikes to kind of monitor that and watch that. But once again, I know we're not living in an exact 100% ideal circumstance. So for this here, kind of what we looked at was, you know, say for aqueous samples, especially because this is what the top assay was designed for, was for aqueous samples originally, you know, that we've got less than 5% of those precursors. Soil samples, you know, they present some different challenges, so we're a little more lenient there. And then also, you know, as we look at detections near that LOD where we don't have, that sound quantification verifications in there, you're going to want to be a little more lenient because we know that those values can have a lot more variability to them. Then also, with your total top results, maybe they'll be, it won't necessarily be greater. They might be a little closer to each other, maybe a tiny bit less, just depending on what happens with the sample. Once again, trying to just give some real world bounds on this. So in theory, yeah, that post-top concentration overall should be much higher, but maybe there wasn't a lot of precursor content. So this was just kind of an assessment that we took upon this to be like, well, maybe within 90%, that's pretty close, if there wasn't much transformation that occurred. And then clearly the other criteria that we had before should still kind of be the same throughout. So looking at the actual data, something that I kind of wanted to take a step back and think about a little bit as we're looking at these data groups and different things, it can also help us look at different types of sources. I know a lot of forensic evaluations, that's kind of where we're emerging into and looking at. So the results from this can, look very different just across your different source materials. Clearly, if there's a mixture of source materials, and then also on top of that, you have to know what your source is. But just to know that, even like looking at the wastewater sources there in the middle, like it's just going to vary a lot depending on where you're at, what the site is made up of. Like Barat had those landfill leachates. Clearly, those are going to show a lot different mixture of analytes than an AFFF impacted site. So just some things to consider and think about when you're looking at this data, kind of in a qualitative viewpoint of what it could help tell you and help describe about what's going on at your particular site or within those particular samples that you're looking at and evaluating. All right, so limitations. Clearly, we don't have anything that's going to answer all of our questions, be the golden ticket, solve all of our problems. Clearly, we all still have jobs and we're still all trying to figure this out. So with top, like I mentioned previously, most of these precursors, or the ones that are going to convert into the carboxylic acids, the PFCAs. So, that's not going to represent what's going to happen in the natural environment. With a top assay, you have a really high pH, you're using strong oxidizers. So we know most of our sites are not going to have those conditions. But clearly, for purposes of the laboratory, we want those strong conditions to give us like the worst case scenario. Also, with some of sulfonamide compounds, there is going to be some of that one-to-one conversion, but once again, we could probably go into a very long debate about, molar conversions and what does this mean. So that's where, you kind of have to take a step back and not make this super quantitative when we're looking at this, because you can't make a one-to-one comparison with different analytes and what they convert to and the total mass. So we're not closing the mass balance here, but and then some of these, form a mixture, and some, with some of these it's just an estimation, and some of the conversions aren't one-to-one. And especially with, like if you look at some of those different branched ones, they're going to convert into two different analytes, or, there's a myriad of possibilities, right? It's not straightforward. All right, so let's look at some data from this project. So, and talk to you about the bounds and criteria that we put on this data, so we could uniformly look at a larger data set and figure out, like, what is this telling us? Does this have precursor? Does this not have precursor? And, I'm going to give you this example, this framework that we developed here. I'm sure we could go into a very long debate about what it could or should be instead. But, at the end of the day, we got to make some decisions. We got to move forward. like I said, if we were all together in the same room, I'm sure we could have some really great discussions about what this should be, could be, and, you know, create some consistency across our industry. I'm sure that's something, you know, we've been striving for with PFAS from the get-go. So, like I said, I'm sure we could have some really good conversations. So, like at the top there, you start with your sample out in the field. You're going to collect enough sample so that the laboratory can do your standard PFAS analysis and then also perform the top assay digestion and analyze the samples. From there, we're going to get the results back from the laboratory there in those gray boxes, and then that's where we come in to start assessing the data. So we've got these different steps and checks along the way to figure out how we're going to use this. So QC criteria number 1 is our the PFSA concentrations in the top. You know, what's that ratio between the top assay and then that original analysis? Here we've got a plus or minus 30%. Once again, this is kind of just giving some real world conditions on it because we know things can happen, right? Despite all of our best analytical techniques, you know, you could have split samples and there's just naturally going to be variability. So within that, you know, does it pass that criteria? Well, if it doesn't, clearly this is when it's saying it doesn't meet our QC criteria because something else is going on. Because in theory, those should be fairly similar. So then in the event that your data does pass that criteria number 1, then you start looking at, did our precursors that we can quantify in our original analysis, did those disappear? And if those disappear, that shows that we had a complete oxidation. Now, I know we could probably go and debate some of the finer points of that, but overall, with what we have available to us, if those precursors that are, you know, detected by standard techniques shows that things were oxidized. And yes, we've got like the 10% for solids criteria, the 5% for liquids, because once again, we're dealing with real world samples. We want to give some consideration for that. So, okay, if it meets that, then yes, we can go on to do this evaluation of our precursor mass. Once again, do not take this as, you know, the final answer, but this is just to help give us an assessment to see if precursor mass are in these samples. So there we've got our little equation just to do the comparison of from what we got from the top assay and subtract out some of those groups that were from that original and assess that over the total mass that was in the original. And when I say mass, I mean the analytically detected mass. And so then from there, based on that evaluation assessment of precursor mass, you know, you look at how much was there, how much percentage change was there. So was there less than 30%? Well, you know, probably not much precursor mass, you know, or a negative precursor mass, sorry. So did that result, you know, change significantly? That 30%, you know, can't really tell, like if you're going beyond the bounds of that. If you've got that plus or minus 30, hey, we've got something here to look at. So with that, just kind of looking at assessing these masses, I have all the ratios here and some data, some real examples to go into and kind of look at some of those things that we know samples can, you know, the challenges that the samples can present for us. So let's move forward to some soil. So for this first heat map here with, and once again, this is with the soil samples. So we know there's going to be more challenges just with that matrix in itself. Prior to oxidation and just that native PFAS analysis, there were PFCAs, there were PFSAs. And then, you know, you can look at that post-oxidation and you do see some increase in the PFCAs, but there's also increase in the PF assays. So they're up at the top. If we look at our total metrics, it didn't meet criteria. So here, based on this initial assessment, it's saying the data is not usable due to the QC failure because of those sulfonic acids changing between the two analyses. Now, granted, I'm sure we could probably go back and do some other analyses if we had other, if we had more sample mass. Once again, because these are environmental samples, I bet you if we did it again, it might not be exactly like this, or we could, do a little further digging to see what's going on or why those increased in that case. I mean, were there some associated QC that didn't perform well in that batch? I can't tell you that here today. If anyone wants to dig deeper later on, we could go back and forth offline from this and maybe do a further examination. So here's another soil example. Once again, it didn't have many detections. As you can see in the little heat map there, there's some PFAS and a little PFPA, and it's pretty small there. It's a light orange based on our key there. So based on doing those assessments, there really wasn't much change. So overall, that was telling us there's probably not a lot going on, or at least in the precursors that we're going to be able to pick up. And it's not enough change to really say with any certainty that we have precursors. So here is another soil sample. And once again, it's the prior to oxidation, the detections are pretty, I guess, simple might be the word to say here. You have PFOA, PFHXS, and PFOS. But then you look over at the post-oxidation and you see, a handful more of the PFCAs crop up. And so though, based on the assessment there, we have over, 41% potential precursors based on the little assessment that we made. And, the assessment criteria is looking pretty good. So here, we could safely say it looks like there is, potential for some precursor mass to be in this particular sample. All right, so now to go on, like I said, with soil, there's a little more complexities that can happen there. But now going on to groundwater, kind of the purpose of what this was more so made for, let's take a look at some of those examples. So here, this, prior to oxidation sample, has a few more hits of things. It's got some FTSs in there, a little more unique profile and diversity in the analytes that were detected. But then after the fact, you will see that it looks like the top assay performed pretty well because that 6.2 FTS is gone. The PFCA is increased like anticipated. The evaluation of the sulfonic acids before and after, it's pretty similar. So, but that whole mass overall comparison of potential percent of precursors, it was a little on the lower end. So, there wasn't a huge uptick. It looks like everything worked great from an analytical standpoint, but there's not a lot of change. So we, with this assessment that we've put on it, we didn't want to say that it was unlikely. We wanted to say that it was unlikely that there's precursors here. Another example, once again, looks like, all of our precursors converted. So we had a good oxidation, that happened here. But the PFSA is increased. It doesn't look like it really did too much. I was just maybe the amount of what was detected. But once again, that potential percent of precursors wasn't jumping out too much. Again, it wasn't, above that 30%. So we're still saying here unlikely just because, of the uncertainty and variability just within the analytical methods. So, we want those higher percentages so we can say with more confidence, hey, it looks like it's here because, like I mentioned before, nothing is really a one-to-one conversion here. We're just trying to do our best to capture more mass and to see what's going on. Here is another groundwater sample that didn't meet the QC criteria. So just to show here, I mean, things converted, but there wasn't, I mean, that amount of potential percent of precursors is really small. And then also just the comparison of the PFSAs wasn't as good as, didn't meet our criteria. And then I have one surface water because, I know with a lot of the projects that we're working on, there's also, a lot of concern of what's entering into these surface waters. I included this one because we could say, potentially looks like we have some precursors. Once again, it's all these qualitative statements, right? Because we have some data, but it's not going to give us that 100% certainty of what's going on here. And overall within what was contained within this sample, it was primarily just the increase in PFCAs that made the big difference here. That initial analysis didn't really see any of those other precursors to watch them, disappear through analysis. But that uptick shows that there were some other ones that clearly we couldn't detect here in our standard analytical suite. And then just to round out everything that, we were looking at the site, I wanted to show a sediment example, which, those of you folks in the lab trying to deal with these, I feel for you, because they present a lot of their own unique sloppy challenges to deal with. So in this case, for this one, I find it a little interesting to look at here. This would be one that I would really be interested to do further, if there were the option at the time to do further work on to see what was really going on here. Because that potential percent of precursors is pretty high. Except for just it didn't meet criteria on the sulfonic acids, which, if I were to honestly look at that total PFAS post-top versus pre-top, that's pretty high. So, maybe there might be some consideration that plus or minus 30% on those PFSAs is not appropriate here because there was so much mass. Once again, I would love to have further discussions on this because, once we all work with all these laboratories and get the data, we have to figure out what to do with it. And, we're all still figuring out some of this stuff. And I think, with a community like this, we could have some really good ideas to share together to figure out, like, what do we really want to do with this? And, to create a meaningful story of what's going on at these places where we're collecting all these samples. And then once again, here is another sediment sample that didn't meet QC criteria. But I find it really interesting that potential percent of precursors came out negative. But once again, like you could see one of those sulfonamides, it was still crept up, but everything increased. So once again, would that be something worth going back and, doing a reanalysis of to see what happened? I don't know. Like I said, you can see between those two heat maps, there's a lot of change, right? Is it meaningful change? I don't know. I mean, clearly it didn't meet, the criteria that we set forth, but clearly there's a lot of change going on there. So, once again, if we didn't have constraints and could be research scientists all the time, I'd love to go back and dig into that more. Okay, so something else interesting here. We also were able to do AOF analysis for a lot of these samples. And so clearly I don't have good sample names here because of just confidentiality reasons. But I wanted to show just some of the different assessments of the samples, the percent precursors that were, calculated here. And then in correlation with that, its respective AOF concentrations that were reported. And clearly, AOF does have its place, and I'm always interested to see more data sets with this because, for the most part, those of us working on these projects, this isn't something you do every day on these because, that's not what's being paid for to do. But I thought it was really interesting because clearly with this, we're on different orders of magnitude of detection. We're doing in micrograms per liter, which with most of our PFAS, specific analyte analyses that we're dealing with nanograms per liter. So trying to make direct correlations can really be tough. If you have any differing opinions, I would love to hear that, because I personally struggle. Like, how am I supposed to have this create a meaningful, picture of what's going on? You can see here with this, we have a variety of reported results, but even if you look there in the middle with that AOF detection of 26 micrograms per liter, the percent precursors assessed was 9%. And our assessment of that mass is precursors were unlikely because it wasn't much of a change. Yet that AOF concentration makes it look like, whoa, there could probably be something else going on here. And yet I also realize none of these can be a direct comparison. It's still, it makes me curious as someone working in these. Is like, what could this really mean? What's going on here? Yeah, and then even in that blue sample over there where it's the potential for precursors, that concentration, 12, granted, that's a lot higher than, the 1 or the 2.7 or the 2.9, which I know, you're getting down towards some of the detection limits of these methods. It's still a lot lower than some of those other ones. So it just, it creates a lot more questions in my mind than answers, which, once again, it's kind of how, we're all working through with PFAS one way or another, whether it's trying to figure out what analyte list we need to do or what method and so on and so forth. So like I said, once again, it's a lot more questions, right? Yeah, but I couldn't find any good trends or correlations to give you some pretty visual example, but still, nonetheless, I wanted to show you with this groundwater comparison of kind of just looking at what's going on, because we did have that data to look at with it. So some key takeaways. As we talked about some of the limitations of top, we're really looking, it's a focus on the concentration of these PFAA precursors in the sample. It's just some conservative estimates. Once again, even though we're getting quote quantitative data, we're really using this to make a qualitative assessment of what these sources could have, looking at them in, this profile of PFCAs that the top assay generates. Something else that it could also do is just, giving us that positive or negative, results overall. I love quote PFAS free because, it's broad has shown all these other things and who considers what a PFAS, right? But still, by doing some of this, you could really capture some of those other unknowns to see whether or not you have some PFAS content or not. And then once again, top has its own limitations. It's not going to convert these unknowns into something that is known necessarily. There's still other variables there that we just can't directly measure. So still within that, I think it's good that we start looking at this with some bounds and try to figure out, what this data really means for us. Is it going to cure everything? No. But once again, it's getting us a step closer to seeing what else could be in these samples that we're trying to make decisions on. Big picture. So with that, I thank you guys for letting me come chat. I'm sure there could be lots of good questions. Like I said, a lot of good discussion we could have here.
Great. Tiffany, thank you so much. We do have a couple questions in the chat.
I am sure.
The first one says, we have done tests on sulfonamide precursors, single component, pure in solution. We've sometimes seen PFAS show up in post-top. It's not consistent and it's not very high, but it's there. My suspicion is that top is not as simple as we think it is, and sometimes variability in pH, temperature, and time can lead to interesting results. I've definitely seen that as well.
Yep. No, and 100%. I mean, within some of this, it was a generalization, right? In general, it converts the PFCAs because that's what we see the most of. But yeah, I'm not gonna, I wasn't gonna say 100% it's not going to. When we were looking at our actual evaluations, it was approximate, right?
Right. Yeah.
So
The
it's a
next
big
one
black
is
box.
it is. The next question is for the top analysis, which analytical method is being used? 537 mod, 1633, and how many pre-top components are being analyzed?
So from my own experience, I know it's going to be laboratory dependent. A lot of times folks have been using, and clearly over time, for the majority of time, it's been like a 537 modified, right? Folks are just, within the past few years, doing 1633. So I believe with this data set, it was a modified one just because of the timing of when it occurred. And then also you can ask some of my lab friends. I know some of them will give caveats if you're using more of a 1633 method, because there are some challenges with that. So I've had a lot of discussions back and forth with different groups about that. So it's not going to be a one size fits all. And because clearly top isn't a standardized method. I mean, we're going off of, Dr. Houtz's paper from 2012 when she was working with Dr. Sedlak. And so, there's no standardization there. So it's going to be lab dependent.
Right. Another question was, is there a resource for the PFAS periodic table for reference in the slideshow? And they found it very interesting.
I would have to, well, clearly it'll be shared with this, but within our own tools within Jacobs, we have a whole bunch of different ones. Clearly I didn't crack into any of, I mentioned some of the forensic stuff, but yeah, we have a lot of different versions of that. But I would have to check internally to see what is available for public consumption there.
I'm curious with respect to the samples that didn't meet like analytical QC requirements, especially with soils and sediments.
Yeah.
Did you find any correlation to the physiochemical properties of the soil itself or sediment? Have you kind of looked at co-contaminants and just the properties themselves of the
Well,
soil?
unfortunately with this site, like it was a PFAS project, right? So there wasn't a lot of those other competing contaminants that we were looking at in this investigation. I would have to go back and look through the project files to see if we did any of those other more parameter style tests that we do with a lot of our PFAS projects. So I'd have to go back and look at that. I don't have that, at the tip of my tongue for today. But you're right. Some of those characteristics can make a huge impact. And once again, that's kind of what I was alluding to when we were looking at some of this. It's like, I would want to look at a lot of this deeper, right?
Yeah, definitely there could be some reasons to tweeze out if you look at other properties as well. Another thing I was just going to mention is that I know CERTIP and ESTCP programs have funded a lot of the research with respect to top assay and optimizing it for soils, in particular, for solid matrices in particular. So there are some updates to that original Houtz paper that had been published, so that could give some valuable information, especially when it comes to the additional QC elements that you could add to the top assay to make it more robust and from a quality standpoint.
Agreed. But once again, it kind of comes down to it's unique lab situation on how they implement that. So not everyone's going to be equivalent like when we were dealing with the standardized method. So yeah.
Definitely. And one still is in the works, from what I understand from sources. TBD, but yes. But it is definitely still on the list of to do for some folks.
For sure.
So I think I don't think we have any more questions. Tiffany, that was a great presentation. We really appreciate it. And you have your contact information is on your slides that will be posted on Denex, so folks can reach out to you if they have any additional questions.
Great. Thank you so much
Okay,
for giving me the opportunity.
Appreciate it. We are going to continue with our third and final presenter, who is JP Verheul. He is a senior chemist and leads Enthalpy's technical solutions team for high-res mass spectrometry and PFAS analytical surfaces. He holds a BS in chemistry from the College of William and Mary and has more than 20 years experience with analytical chemistry for environmental samples. JP evaluates market trends to help optimize analytical programs and routinely supports a wide range of complex project types, including soil, solids, solid waste, commercial and industrial wastewater monitoring, drinking water supply, air emissions, and site assessment and remediation. With that, take it away, JP.
Thank you very much. And thank you all for sticking around to the end of the entire session. I am sorry that we're not all together and I can't see you all jumping and shouting in enjoyment that we're doing another presentation on analytical chemistry. So with that, please take your seats and we'll get started. Not much to say about me. Thank you very much for the introduction. There's my big old head right there. I do lead our technical solutions team at Enthalpy Analytical. It's a great group of folks that focus on providing custom technical solutions for complex analytical projects circling around PFAS and high-res mass spectrometry. So the focus of the talk was really meant to be on ultra short chains, and we're going to do that. But I thought what might be helpful to get us there is to kind of review very, very briefly foundations for PFAS analysis on some of the more traditional methods, explain some of the challenges we have with those methods and how we as a laboratory can work around those challenges to develop this novel ultra short chain method. So what you see on the screen here is an overview of the different analytical methods for analysis of PFAS available at Enthalpy and really any commercial laboratory. Everybody's going to have a little bit of a different flavor, but I like to show this slide to highlight that there are a lot of different ways of going about how we evaluate and quantify PFAS. Again, it's a list of over 15,000 different chemicals, possibly more depending on how you characterize them. So difficult to quantify, and one of the most basic concepts here, and probably a review for everybody, is the use of what we call isotope dilution. So again, very quickly, when we talk about isotope dilution, what we're talking about is the use of carbon-13 as opposed to carbon-12, the most abundant form of carbon known to us. Carbon-13 has 6 protons and 7 neutrons. 6 and 7 is 13. That 7th neutron gives it just a little bit more mass than carbon-12. And that's really important to us in the laboratory. So when I say that, what I mean is what we're looking at here is 2 versions of PFOS. The one on the left is traditional PFOS, probably manufactured by an industrial manufacturer. On the right, we have what's called carbon-13 PFOS. 2 of the carbons in this molecule are carbon-13. We call this a radioisotopically labeled standard. And the primary thing to keep in mind here is that the carbon-13 PFOS is just a little bit heavier than carbon-12. Again, this is important to us in the laboratory because it means that we can actually resolve carbon-13 from carbon-12 and use that radioisotopically labeled standard to help determine what kind of recovery we're getting for our target analytes. What do I mean when I say that? So I imagine this is old news for just about everybody on the call, but in case it's not, this is sort of the theory behind it at a very high level. So in the laboratory, let's say the laboratory receives an unknown sample. We want to quantify PFOS. For the sake of argument, let's say there's 100 nanograms of PFOS in that sample, but we don't know that. The laboratory will add a known concentration of the carbon-13 isotopically labeled standard. In this case, 2 nanograms. So we have 100 nanograms of PFOS. Again, we don't know that. And then 2 nanograms of carbon-13 PFOS. That's a 50-to-1 ratio. In the laboratory, and in the theory of isotope dilution, what I like to highlight is that this 50-to-1 ratio maintains throughout the entire process. So the sample is extracted, it's cleaned up, maybe using carbon or NB-carb. It's concentrated after extraction. Methanol concentrate is concentrated and then analyzed. At each step, the ratio of the isotopically labeled standard to the target analyte stays the same. When we finally get to the analytical stage, the analyst says, hey, great news. We have your PFOS concentration. It's 25 nanograms. We say, okay, but what was the recovery of the carbon-13 standard? Oh, well, we only saw 0.5 nanograms. We initially put in 2, though. 0.5 is a fourth of 2. So that means we saw a 4-fold reduction or suppression throughout the entire analytical process of carbon-13 PFOS. Basic theory of isotope dilution is that carbon-13 PFOS and carbon-12 PFOS behave the exact same way throughout this process. So if we know we've got a 4-fold reduction of carbon-13, we know that this PFOS result of 25 nanograms is also suppressed by a factor of 4. So we have to multiply this by 4. 25 by 4 gets us to 100. So this is, again, just a brief overview of how isotope dilution works. So that's the first thing I wanted to cover. The second is something called solid phase extraction. So solid phase extraction is written into pretty much all of the established EPA methods at this point, 533, 537, 1633. It's very time consuming. And I love to show this picture because I think it's really helpful to see what happens in the laboratory. So what you're seeing here is a photograph of manual extraction. Now there are automated extraction systems. In fact, there's one back here on the bench that's sort of out of focus, but for the purposes of going through the theory of solid phase extraction, I like to use this manual manifold. And again, at a high level, basically what you're looking at here is a vacuum pump off to the side that's attached to this big glass vacuum chamber, above which we have a number of little tubes or syringes that are filled with something called solid phase extraction media or weak anion exchange media. The idea here is that the samples are poured through this syringe, which is under vacuum, this vacuum pump, that the liquid portion of the sample will flow through the weak anion exchange media, and the PFAS will be captured onto this media. It will adsorb onto the media. So weak anion exchange, solid phase extraction. This is the extraction step. It's also one of the most time-consuming steps in the entire process. Once the sample has fully gone through or filtered through and the PFAS have adsorbed onto the weak anion exchange media, the PFAS are then recovered using a solvent, methanol. That methanol is then concentrated and sent to the instrument. And it's worth me noting, sorry, I should have said this at the outset, that the PFAS isotopically labeled standards are added to the containers directly right before this solid phase extraction process. So you take the methanol extract over to the instrument, and this is what it looks like in the laboratory. Of course, it's going to vary from lab to lab based on the instrument, but I think you all get the idea. So the sample is brought over in a very small 1 milliliter vial, placed into a auto sampler tray, and then a robotic arm will pierce the septa of that vial and send the sample over to the liquid chromatography column. Now, for those of you who are more familiar with GC mass spec work, you're probably used to seeing a massive copper coil wrapped up inside of an oven. That's your GC. Here, this is your liquid chromatography column on the right-hand side, about 3.5, 4 inches long, very, very small, and packed with a media that will select for PFAS and separate out the different PFAS molecules based on different factors like size and charge. So different PFAS will come out of the column or elute out of the column based on those factors at different times. That gives us a time component that we call retention time. That's our time factor. As those different PFAS molecules elute out of the column, it will head over to the mass spectrometer. So the instrument we use is actually a liquid chromatography tandem mass spectrometer. It has 2 mass spectrometers in series. The first step is that the sample is sent over to an electrospray ionization introduction into the mass spectrometer source. Analytical chemists get pretty upset when you call this aerosolization. It's not technically. It's charging of these small little drops that are then passed through a series of cones to separate out the target analytes that you're looking for, in this case, PFAS. That sample stream then passes through a mass spectrometer, which filters out some of the things that we don't want to see. There's a reaction in the second stage of the mass spectrometer. So a collision cell, these are bombarded or fragmented into tiny little pieces, and those fragments head through the third phase of the mass spectrometer, where they're filtered again and sent to the detector. And on the detector, we're looking at the mass to charge ratio of those individual fragments, again, as a component of time. So just at a high level, the theory behind PFAS analysis by LC mass spectrometry. I happened to be down in the laboratory while they were doing some work. The particular instrument that they were working on had gold-plated quadrupoles. So we talk about triple quad. This is what one of those quadrupoles might look like. I just think it's kind of neat to share what actually happens in the laboratory. So there's a photo for you. Also kind of helps demonstrate why these instruments are so expensive. Okay, so back to the subject at hand. We talk about solid phase extraction. Again, this is something that takes a whole lot of time. I imagine most folks on this call have had to do some kind of PFAS analysis over the last 6, 12, 18 months. You all probably remember a time where when you sent samples to a laboratory, the lab said, yeah, we could run these, but our turnaround time right now is pretty long, anywhere from weeks to months. That's usually because, well, at the time, I think laboratories were at capacity because more labs had to scale up to support the market, but also because this step does take quite a bit of time. And of course, method 1633 does have some restrictions as to what you can do to move this along a little more quickly. And of course, if you're looking at method 1633, you're trying to push maybe 500 milliliters of sample through these cartridges, probably less if it's something like landfill leachate. This is a photo of real world samples, and you can see some of these are just black, right? Some of these samples take days to fully extract. And then upon analysis, you may find that you've got failing quality control parameters that require you to go back to the beginning and extract again. Why am I sharing all of this? Because this is, in many cases, the rate limiting step to providing expedited data. So not too long ago, most laboratories started working on a solution to this, which we call it a high-level direct inject analysis. So direct inject analysis, there's two methods that are frequently cited for this. Method EPA 8327 or method ASTM D8421. Now, both of these are for aqueous methods. There is a method for solids. It's ASTM D8535. But again, just to go through the theory, I thought it'd be easier to talk about the aqueous methods. So 8327 came out a few years ago. It was really more of a screening method. At the time, it allowed for isotope dilution, but did not necessarily have to use it. ASTM D8421, similarly, it's for 44 compounds, does allow for isotope dilution. But the beautiful part about both of these methods is that there is no solid phase extraction. Why are they relevant now? They're relevant now because although these methods may have been around for a few years, when they came out, the analytical technology was not sensitive enough to give reporting limits that are meaningful or on par with where we see solid phase extraction using these methods. That is no longer the case. So there are analytical instruments out there right now that do allow for you to use these methods with isotope dilution, no solid phase extraction, and achieve reporting limits that are on point with method 1633. Most labs have taken a different approach to this. So I'll speak to what Enthalpy has done. Enthalpy has sort of taken the best bits of both of these methods, combine them into what we're just calling a direct inject isotope method, isotope dilution method. We've got an analyte list that's up to 63 compounds now, so we can quantify 63 different target analytes using isotope dilution. Standard turnaround time for most laboratories is 10 days, but the beautiful part about this is that you can oftentimes expedite data. So I would imagine most folks on this call are familiar with the fact that the DoD put a memo out, I think probably a little over a year ago, allowing for the use of screening tools in the field. Direct inject was one of those screening tools that was most frequently cited. Folks were having to wait weeks and weeks to get data using method 1633. These screening tools allow for a much quicker evaluation of what's in the field, and then of course samples had to be confirmed using method 1633. One thing I do like to harp on is that although these can be used as screening tools, they are quantifiable methods. We are using isotope dilution. We are quantifying down to single-digit PPT in many cases. So this is a much more robust method that I think will be used more widely in the future for more than just screening. Okay, so now that we've got some of the foundations on isotope dilution, solid phase extraction, and direct inject, we can actually start talking about ultra short chains. So when we talk about chain length, what are we really talking about? Well, when we talk about long and short chains, interestingly enough, the difference between those two are not necessarily based on the number of carbons in the molecule, but more based on bioaccumulation. So here you can see carboxylic acids. Long chains are considered 8 carbons and longer. 4 to 7 would be your short chains, as opposed to the sulfonic acids, where your short chains are really 4 and 5 carbons, and then 6 carbons and longer would be considered your long chain. Again, this is due to the bioaccumulation effects that we've seen with these different molecules. That is not the case with ultra short chains. With ultra short chains, it is very simple. Basically, 1, 2, and 3 carbons long are ultra short chains. So here's some common examples: perfluoropropanoic acid, or PFPRA, trifluoroacetic acid, TFA. We've already heard about both of these earlier. Also TFMS and PFPRS. Most of the time, these are extremely polar molecules, which means that we have some challenges in analyzing these when we look at historical methods. So these may not present well using something, say, method 1633. Very unlikely that you're going to get great data for something like trifluoroacetic acid using method 1633. We also heard a lot today about adsorbable organic fluorine and total oxidizable precursors. You likely will not have data that are, or not see ultra short chains contributing to the data using either of these two methods. With adsorbable organic fluorine, that method really relies on carbon adsorbing PFAS onto carbon media prior to combustion ion chromatography. These ultra short chains will most likely not adsorb. They will fly right through. So you can see some low bias in your AOF data if you're looking at ultra short chains. And then again, you're likely not going to see this in top assay data unless you're specifically targeting it. And I'm not really aware of any folks who are doing top assay looking for ultra short chains, but if anybody has, I'd love to hear more. So why do we care about this? I thought it would be useful to pull some articles or headlines that are a little bit older to show that this has been a topic of conversation for the last few years. So we've got some headlines here from 2019, 2021, 2023. We know that these are out in the environment. In many cases, they may be the product of degradation, or they may be part of industrial manufacturing. PFPRA, great example of both of those situations. So we know that we have these in most likely household products. So they are out there, they're in the environment, and they're not showing up in a lot of our data sets generated by some of these traditional methods like 533, 537, and 1633. So Enthalpy got into this because we had a client that reached out to us and said, hey, we've got a unique situation and we need some help. That situation was that this client, a PFAS treatment company, had an industrial manufacturer that knew that they had ultra short chains involved in their industrial manufacturing process. They had divulged this to the treatment technology company and also to, I believe it was the local POTW regulator. So it came down from up on high that they should do everything they can to remove these ultra short chains. The treatment technology firm said, yeah, we've got a great technology. We believe that we can remove these, but we need a way to show, we need a way to demonstrate that we are actually removing these. We need a laboratory that can help. Oh, and by the way, we want to put a pilot system on place, and we're going to need data really quickly, like 2 to 3 business days. You guys can do this, right? So this is why I spend so much time talking about solid phase extraction, isotope dilution, and direct inject analysis. We know that we could not use traditional solid phase extraction methods to target these. We know that those methods also don't give us the kind of data that we need really quickly. But the direct inject method might be able to if we find the right solution with it. Again, these target analytes are very polar. So even just the direct inject method, as we had developed it according to 8327 and 8421, was not enough. Fortunately, we've got some great chemists at Enthalpy, and this is what they came up with. And I think everybody will receive a copy of these slides. If not, feel free to reach out to me, and I'm happy to share this. So in short, this is essentially what the laboratory is doing. So taking 5 milliliters of sample, just like you would take with the direct inject method, adding 5 milliliters of methanol with that isotopically labeled standard where it applies. Not every ultra short chain has a carbon-13 standard available, and run it under some slightly different analytical conditions. And the real winner here is the different column. We found a column here that was much better suited for polarity that we see with these ultra short chains. Once we dialed this in and validated this method, we knew that we would be able to provide the type of support that these folks were looking for. And we were. So we had to essentially deploy 2 different direct inject methods to do this, but we did find a solution. We're able to turn samples in 2 to 3 business days, and at this point, the lab has processed thousands of samples for ultra short chains. So that's how we came to develop the method, and a little bit more history of how we use it. What does it actually involve? And also, why do we care? So right now, the laboratory is quantifying 6 different ultra short chain compounds. Those are listed on the left-hand side. We are in the process of finalizing validation for another 7 on the right-hand side by this same exact method. One thing you'll see is that I've highlighted 2 of these, HQ115 or TFSI and PFPRA. The reason I've highlighted this is because although I've said that the ultra short chains are historically do not show up in traditional methods, these 2 can be identified using 1633 or maybe 537 modified, and have been written into DoD screening criteria. So there they are. I expect most laboratories, including Enthalpy, have expanded their 1633 list to include these. We saw a great presentation by Bharat earlier that included exactly this information. Bharat, as always, thank you. Teed me up perfectly. So I think we'll see a lot more attention paid to these 2 compounds, but there are certainly more out there. So what are we seeing in the laboratory? When we first developed this method, we were using some slightly older systems, and you will see that our reporting limits were 700, 750 parts per trillion, up to around 1,000 parts per trillion. Not too long ago, the laboratory did install brand new SciEx 7500 instruments. I'd mentioned earlier that instrumentation has come quite a ways. These instruments are extremely sensitive, and we are able to see much lower, in some cases, single or low double digits PPT for these ultra short chains. Now there is one exception here, which is trifluoroacetic acid. It is not, the issue here is not that the laboratory cannot see low for trifluoroacetic acid, it's that there is just so much background contamination. So I think, Janice, it was you that may have asked a question about this type of contamination following Bharat's presentation, and very happy to say that I've got some slides in here about this. So when we started looking at lowering limits for TFA, we were very surprised in the laboratory to see that we are finding it all over the place, including in what was sold to us as PFAS-free water, some brands or grades of methanol, polypropylene containers, which was a huge surprise because these are written into method 1633, different pipette tips, etc. We've also seen where exposure to high trifluoroacetic acid concentrations can create really long-lasting background interferences or baseline shifts. In fact, the laboratory we manage in Wilmington, it's a DoD laboratory there, has one instrument that was so badly contaminated with TFA that that's really all we use it for now. Other challenges are that high concentrations of other PFAS can create a masking effect. It may be difficult to resolve some of these ultra short chains if you have other high concentrations of other PFAS. And then, of course, identifying and procuring the right consumables, columns, standards, isotopically labeled standards can be a real challenge. So here's a reagent blank chromatogram on some of these ultra short chains, TFSI, TFMS, and PFPRA. Not gorgeous, just looking at the baseline of the blank. But when we start looking at our low limit quantifications, we see much nicer peaks and much nicer baselines. Similarly, for trifluoroacetic acid and then the 2 iterations of TFPA, the baselines and the blanks are not too beautiful, but running the standards, we see something much nicer. And one of those TFPAs, I'm missing data, so I apologize. Because we did talk about contamination, I also thought it would be useful to share this. So this is an overlay of a few different chromatograms we saw of TFA at 300 parts per trillion, 500 parts per trillion, and then also one of the blank studies that we did in some of the polypropylene containers that we had been using for other PFAS tests that showed no contamination for any other target analyte. So you can see right there significant contamination from those polypropylene containers. Again, TFA is ubiquitous; it's all over the place. So I think that's going to be one of the biggest challenges we see with ultra short chains, is how to bring that number down. So some current and recent applications. I just gave an overview of a case study that I think is a great example of where ultra short chains are coming into play in the environment, in industry, as far as treatment technology, and also regulatory, although most folks are not looking at this from a regulatory standpoint. And then we're also seeing a lot of requests for ultra short chain analysis from destruction, pilot, and bench studies, which makes a lot of sense. If you're looking at destruction of PFAS, you want to know, did we actually destroy this stuff? Or did we just break it down into really, really, really small chains that we can't necessarily observe directly using some of the methods that are out there right now? So covered a lot of ground, but in summary, ultra short chains, they are ubiquitous in the industry, in the environment, and all over the laboratory. With the exception of TFSI and PFPRA, most cannot be directly measured using the existing EPA methods that are out there. So you'll want to use a customized method that will account for some of the challenges that we see with ultra short chain, like the size and polarity of these different molecules. And under the right analytical conditions, quantitation limits under 100 parts per trillion may be attainable. I think I saw something similar on one of the slides that Bharat had, so was happy to see that. And right now, the laboratory, at least at Enthalpy, this method is only available for an aqueous matrix, but I believe a solids method will soon be available. And with that, put up my contact information and just say thank you all very much. Happy to answer any questions.
Great. Thanks, JP. Really appreciate it. Great presentation. I think it pivoted really well off of Bharat's earlier presentation. I think Bharat just had one statement about top assay, extending their top assay in the comment section.
There it is.
Yeah. And we have another one. Do the ultra short fragment, what ions are you using to quantify?
Yeah. So Bharat, thank you. Great comment. Really appreciate that. And I may bug you offline just to hear a little bit more. And then regarding the short fragments, yeah, it's a great question. This came up not too long ago at a different conference. So trifluoroacetic acid gets a lot of attention because although it has a transition ion, not really a conformation ion. So we use whatever ions we have available to us. Not a whole lot for the ultra short chains. This is where the importance of the isotopically labeled standards will be so critical.
Okay, great. I'm looking for some more questions. Do not see any. I think we're good. Okay. Right. Well, thank you so much for your presentation. It was excellent. It was a great way to, I think, end our PFAS session. I do not see any additional comments. I'm sure we're going to keep the tradition going and next year have, whether it's in person, which we all cross our fingers for, but if not, we will always continue on with webinars in the future, and hopefully I'm sure we will have another PFAS session. So, I always appreciate people's feedback on, what other topics you see with respect to PFAS or any emerging contaminants that you would like more information on and possibly include in a future webinar. So we would love to get that feedback from everybody. With that, just reminding everybody that all these presentations will be on the EDQW's Denix webpage, along with all the slides for you guys to take a look at so you can have as reference. And feel free to share with other people in your organizations. Again, everyone did an excellent job. Thank you all so much for taking the time out of your day to participate in these webinars. We really value everyone's input and great discussion, and look forward to talking with you all again in the future. Thank you so much.